that we'll look at for the 32-bit processor architecture: the modes of operation. So different modes that this processor operates in. The basic execution environment, a unit inside the processor called the floating point unit, and then we'll look at the Intel microprocessor history. So here are the two of the different modes of operation that processor can operate in. The next two will be in the other slide. So the 86 processor has three primary modes of operation. The first one is the real address mode. The real address mode is the native MS-DOS. It's useful if a program requires direct access to system memory and hardware devices. And it's not currently supported by Windows. Everything is running in one executable space when we run in real address mode. And we'll talk about what that means in a second. So I don't have there's a mode that we'll look at in a minute that's called protected mode. So here, what's important about this is that when you're in real address mode, everything is running in one executable space. That means that if you have four processes that are running, they're all in the same space, same memory space. And if one of those processors, for some reason, goes and writes on top of the address that's running this process, and it's going to crash this process. And so protected mode, which is on the next slide, protected mode segments, and it has a space for each of the processes. So this is why this is not supported by Windows, because we don't want everything running on the same space. Then there's the system management mode. It's a special purpose operating mode provided for handling system-wide functions like power management, system hardware control. It's intended for use only by system firmware like BIOS, but not by application software or any kind of general purpose system software. So this is the system management mode. Here's the protective mode. It's a native mode to Windows and Linux. All instructions and features are available. Programs are in memory segments. So each process that runs is in one segment, and it's not going to go in and write on the other programs that are running. So they're separate, they have their own little houses, and you can't overwrite them. And then you have the virtual 8086 mode. This is a hybrid of the protected mode. It's a hybrid of this. And it's for backward compatibility, meaning like when we came out with the 32-bit processor, we had to be able to run 16-bit applications on the 32-bit processor. So in the 64-bit processor, we have to be able to run 32-bit applications, and that's why this is used, so that we can run applications that were built on smaller processors. Basic execution environment. So in the next few slides, we're going to talk about addressable memory, general purpose registers. So we're going to start getting into registers, which is what we'll use to code in assembly language. Index and base registers, specialized register uses, status flags, floating point, MMX, XMM registers. So addressable memory. In a 32-bit processor that is running in protected mode, a task or program can address a linear address space up to 4 gigabytes. Linear address space means that you have one address after the next after the next. Extended, it is a 32-bit processor, is extended to 64 gigabytes starting with the P6 processor. So again, it's running in protected mode and can address, the program can address a linear address space of up to 4 gigabytes, but extended to 64 with the P6 processor. Real address mode programs can only address a range of 1 megabyte. If the processor is in protected mode and running multiple programs in virtual 8086 mode, each program has its own 1 megabyte memory area. So if the processor is in protected mode, remember we're running in segmented area, so each segment has 1 megabyte memory area. Where a 32-bit processor in protected mode has 4 gigabytes, extended to 64. Okay, what you see on this slide is the registers that are available on the 32-bit processor. And these are the names of these are the register names that we'll be using when we program in assembly language. So these right here are general purpose registers. We're going to just use them for arithmetic, logical operations, saving addresses. eFlags register, we'll look at that in detail in one of our slides, where we actually save flags that tells us, like, did we have an overflow in our operation, or did our operation give us a negative number, or did we get a 0 when we completed this operation. This register here is the instruction pointer. I'll also go over what that means. So each one of these registers is 32 bits, right? Because this is a 32-bit processor. Okay, that's how much memory we have for each one of these registers. And we actually get to divide these and use part of those. We get to use all the 32 bits, or we get to use 16 or 8, and we'll look at that in the next slides. And then here, these are 16-bit segmented registers that we also have access to when we program in assembly language. This next slides will look into detail about these registers. And even though I'm going to tell you a lot about these registers, you're just going to learn about them as we program. So don't try to memorize all this. This is just like a general overview over the registers, okay? You don't need to memorize all this information right now. So each register holds 32 bits. And we have 8 general purpose registers that we're going to be using. And then this here just describes what we will be using, all the different functions that we can use the registers for. So we'll be able to store data in the registers, do arithmetic operations, logical operations, data movement, and we can put arguments and return values from functions in the registers. Okay, so when we look at this slide, we're looking at just one of the general purpose registers. So the one that we're looking at is the EAX register. This EAX register, like we said, was a 32-bit register. So from here to here, we have 32 bits available to us. If we just need 16 bits and we don't need the whole 32 bits, then we can access this area here of the register, these first 16 bits, by referring to that part of the register by the name of EAX. So for example, in assembly, I can, to assign something to a register, I would say move into EAX a value. So if I move the number, the decimal value 10 into EAX, it's going to use 32 bits for that 10. I can also move it into 16 bits. I would do the same thing, but I would just say, I would just use the name AX. And then I can then further divide AX into 8 bits, and I can say AH, and then that would access this part of the register. So you're accessing this part of the register, or AL, you would access this part of the register. So you can use either one of these names if you just need 8 bits. Or let's say that you have a value in AX and you just need the first 8 bits. So you have 16 bits in AX and you just need this first 8, then you can access it by using the register name AH. So like we said earlier, the names, let me erase this here, the names of these, the very first 4 general purpose registers are AX, EAX, EBX, ECX, and EDX. Again, I don't want you to memorize this. We're going to go over this as we start programming chapter 3, okay? This is again just like an introduction of how the registers work, and we'll do all this again, and we'll keep working on it in every single chapter. So if I want to save values into a register, like I want to store values in a register, I can store them in any of these registers here. So if I'm already using EAX, then I will then use EBX. If I'm already using EBX, then I'll use ECX, etc. Now, again, with these, if it's EBX, then it'll be EBX, BX, BH, BL. If it's ECX, this would be CX, CH, CL. EDX, just change the A to a D. And that's what this chart here shows you. It's just the name of the register and how many bits you have available for that register. So take out the E in front and you have 16 bits. Take the first letter and put an H in the back and you have 8 bits. Same thing, put an L, it's the lower half of your 16-bit register. Okay, here we're looking at what we call the index and the base registers. So right here, this one, these two that end in I are index registers, and this is a base pointer and a stack pointer. This is so these registers right here, these are the next 4 general purpose registers, only have a 16-bit counterpart. So you can have access to 32 bits or you can have access to 16 bits. We're going to be using, in our programs, we'll be using the stack pointer. towards much later chapters. I think probably maybe starting chapter 5, we'll use the stack pointer. And we're going to learn that this is a register that we don't want to ever change with anything, because it's always going to be pointing to a stack that keeps track of the current, like the current instruction, or the current, not the current instruction, but current values that we're manipulating. It's kind of hard to explain. And then so that's the stack pointer. And I think that's all I want to say about this for right now. So this, you just know that these 4 general purpose registers just have a 16-bit name. They don't have 8-bit names. As you start programming in assembly language, you'll find out that there's going to be some registers that are used specifically for certain things. For example, I'm not going to go over all these, but I'm just going to give you an example about the ECX register, okay? So the ECX register can be used to move values into it, like, move a 10 into it and save a value of 10 in it. But when you get to learning about how to do loops in assembly, the ECX register is going to be what keeps track of your loops, the counter of your loops. So if you have a loop, let's say this is the start of the loop, this is the end of the loop, right? And let's say that this loops 5 times. Then in assembly, we actually have to set the counter for the loop. And we have to say, okay, this is going to loop, this is going to iterate 5 times. And then automatically, with the instructions for looping, every time that, there's my kitty, I don't know if you can hear my kitty meowing. Every time that you make one iteration, so you go around once, this loop counter automatically gets decremented by the assembly instruction. So the assembly instruction will automatically decrease ECX. So you'll have to know that ECX, when using a loop instruction, decrements this register so that you don't mess with that register. You can't change that register. So there's all these specialized registers that you're going to be learning about them as we program. You don't have to memorize again any of this. It's just an introduction to what you're going to see in the rest of the class. The EIP register is a really important register. It's the instruction pointer. As a program is running, the instruction so sorry, I'm trying to move my cat. So as the instruction gets, as one instruction is processed, another instruction is the address of the next instruction is on the EIP register, which is the extended instruction pointer. So let's say, how to explain this. So here's a stack, and here's an address, and EIP points to this instruction, okay? Let's say that this is the instruction, the next instruction that's going to be executed. So that's where EIP is pointing. So that's another register that's specialized that we don't want to, change it. We don't want to move any values into it or use it for arithmetic unless we're actually wanting to move that instruction pointer for some reason. And then another specialized register that we'll use is the E-flags register. And the E-flags register, so you have 32 bits, but each bit actually is a flag. Okay, now I'm not going to put these in the right order because I don't remember the order of all the flags, but we're going to say, for example, that there's a flag. We'll look at the flags in the next slides, but there's one flag that's called the 0 flag, okay? 0, ZF. And let's say that it's in this position, the least significant bit. Fiona, move. Then if I have a calculation, like let's say that I decrease my variable, and when I decrease my variable, I'm at 1, I'm at 1, yeah, and I decrease it by 1, so now I'm at 0. So since I decrease my variable and I'm at 0, it would set the 0 flag to true. So it would just have a 1 there. And the reason that I have flags is that we're going to see that we get to actually, when we program in assembly, we get to check these flags, or there are instructions that check the flags. For example, when we do Boolean operations like true, false, there'll be instructions that will be checking if it's true or it's false, or it will just check these flags, okay? And the way that it does true, false is certain flags that are set. So each flag is a single binary bit. So this could be the 0 flag. This here could be the, I'm trying to think of all the flags right now on top of my head. Negative, if we get a negative, if we do an arithmetic operation, we get a negative value, that would be a flag to tell us that it was negative. So that could be this flag right here. So each one of these is just a separate position, and we're not reading like the whole number, okay, like we read the whole binary number. Okay, so here are the flags that I couldn't remember earlier. And again, we're going to go over all these flags again later. You don't have to remember this. But so each one of these positions will actually will set the flag, and you don't have to know which position it is. We're going to be looking at the different flags, which we just have to, we don't write the flags, the system writes the flag. So if for some reason we have an unsigned arithmetic out of range, so if you remember the range of a byte, right, if we like it was 0 to 255. So if we go out of range, like, you know, if we try to write the number 300 for one unsigned byte, then the carry flag would be set to a 1. Let's say that the carry flag is here, CF for carry flag. Then it would, at first it would be 0, but since we carried, it would then be changed to a 1. So we have assigned arithmetic out of range. That's the overflow flag. Signed flag results in a negative number. 0 flag results in a 0. And then the auxiliary carry and the parity, we don't use as much. So I'm not even going to go over those. Okay, in this slide and in the book, it's going to talk about the registers that are used by the 64-bit and 128-bit registers, the names of them. And it also talks about the 8 80-bit floating point data registers. And we are not going to be using those. That is outside the scope of our class. But you will see in the book where it talks about the MMX registers, which will be like MM, and it'll have a number 1, 2, 3, 4, 5, like that, and the XMM registers. Again, we're in this course, we will program everything for 32-bit registers. We're not going to look at the 64-bit because it's just hard enough to program for the 32-bit that I don't want anybody to be confused. So we're just going to stick with 32-bit, and that's it. But this is just so it is in your book so that you're aware that's what these names are. And this is the end of this video. In the next video, we'll talk about the 64-bit processors. I have a YouTube video for this section, components of the microcomputer. So looking at all the components inside the computer, and then I'll discuss the input-output system. And there is just 2 videos for chapter 2. Thank you, and email me if you have any questions.